Hello everyone, we'll now be doing past paper questions of entropy, and I have compiled around 5 questions of the past year CIEs, the recent 5 years, and I think this will give you a very good idea of how they ask these kind of questions and how you're supposed to answer them. Okay. Let's start with the first one. This is from May-June 2025. The first question asks, define entropy. Now, for definitions, they usually have different answers in the marking scheme for every year. But one definition that you can go with, and it will work for all of them, is that you can just say it's the measure of the disorder and energy in a system. So entropy is just the measure of disorder. You can also write randomness and other similar words. But the main point is that it's the measure of the disorder and the energy in the system. Okay. Let's go to the next one. This one says, figure 3.1 shows how the entropy of a pure substance changes with temperature. Now, this graph, we have seen it in our lecture, and this is a very similar graph. So here we have 0 Kelvin, and when you increase the temperature, we are increasing the entropy. And why are we increasing the entropy? Because we are increasing the randomness in the system. We are making the particles more disarranged. We are increasing the distance between the particles. And remember, we said that this point over here is where the particle is melting, and this point over here is where it's boiling. Identify the process occurring at each of the temperatures T1 and T2. So we have just answered this already. I explain why the entropy change, delta S, at T2 is bigger than the entropy change at T1. Now let's look again at what's happening at T2. For T2, you are going from a liquid into a gas. And for T1, you are going from a solid into liquid, right? Now, when you go from a liquid into a gas, in a liquid, the particles are not very close to each other and not very far to each other, right? But in a gas, the particles are very far to each other. But when you go from a solid to liquid, in solid, they are packed quite close to each other. And in the liquid, it's not much different from a solid. They are just slightly separated. You can see that the change from liquid to gas is more than the change from solid to liquid in terms of the space between the particles. When you go from a liquid to gas, you are separating these far more than when you go from a solid to liquid. So that means that the entropy change for T2 will be bigger. And why will it be bigger? Is because you are separating the particles much more. So you can write that the change in the disorder from liquid to gas is more than from solid to liquid. Yeah, right. Next one says the equation for the reduction of iron oxide by carbon monoxide at 450 degrees is shown. So we have this equation over here, and they've given you the delta G. This is the Gibbs free energy change. Table 3.1 shows the enthalpy changes of formation and the entropy for some substances. So we are given the formation values and we are given the entropy values. Remember, this entropy values is for the single substance. We say that each substance has an entropy value. Use the data in table 3.1 to calculate the entropy of carbon monoxide at 450 degrees and show your working. Now, the way we can solve this is that, first of all, you should remember this equation which says that delta G equals to delta H minus T delta S. This is a very important equation. Now, we have the value for delta G, which is negative 36.2. Do we have the enthalpy change of reaction? Remember, this H over here is the enthalpy change of reaction. We are given the enthalpy changes of formation values, which we can then use to find the enthalpy change of reaction. And delta S over here is the difference between the entropy of the products with the entropy of the reactants. So delta S equals to delta S of products minus delta S of reactants. And we have the temperature given as 450 degrees centigrade, but obviously we have to convert this into Kelvin. So let's go with the first step of this. So step 1 is to actually find this delta HR, which is the enthalpy changes of reaction. Let's rewrite this equation over here. So I have rewritten this equation, and let's try to find out the delta HR of this reaction. What we can do is, because we are given the enthalpy change of formation values, remember, what does formation mean? Formation is the enthalpy change when 1 mole of a substance is formed from its elements. So you are forming each of these, this, and this. But remember, for iron, for an element, the enthalpy change of formation is 0. So the HF of this will be 0. But you can form this one, and this one. So we can draw a Hess cycle over here. Also, one tip while drawing the Hess cycles, in your calculations, it's not a must to know what's over here down, right? You can just go with the normal values that you are given, and you don't have to bother and figure out what's going to be there at this bottom part over here, right? Are we given the enthalpy change of formation of iron oxide? We are. We have been given, this is negative 824.2. So this is negative 824.2. The one for carbon monoxide is negative 110.5, but that's for 1 mole. This one has 3 moles, so we will multiply this by 3. Then obviously for Fe is 0, and for carbon dioxide we have been given the formation as negative 393.5. So this is negative 393.5 times 3. So this is what we are trying to find. So we can make an equation for this, that's this one plus this one plus this one equals to this one, because you see how the vector diagram is going. These two arrows plus this arrow gives you this arrow. So you should get the answer as negative 24.8. By the way, the reason that I didn't do the calculations is that I don't want to waste your time and my time in doing these calculations, but I feel everyone should be comfortable enough in doing these calculations and knowing how to get this x over here. So when we get this one, we have this as negative 24.8. What will be the temperature value? The temperature value will be the degree centigrade one for 50 plus 273, and you get your answer as 723 Kelvin. So this is the value that we will be using for our T. So delta G equals to HR minus 723, and let's say delta S is X. And how much is our delta G? Delta G has been given as negative 36.2. So we get this one as negative 36.2. Then X should be equal to 0.01577. Now we have to be very careful here. Remember, all these values were in kilojoules. This was in kilojoules and this one was in kilojoules. So the answer that we get over here is also in kilojoules, right? So this is kilojoules per Kelvin per mole. Now what we can do is we can multiply this to joules so that we have a consistent data. So when you multiply this by 1000, you get 15.77 joules per Kelvin per mole, right? Now we can find the entropy of CO because we have found the total entropy change. This is delta S. Now we can expand this delta S, and remember the formula for entropy change of the system was the total entropy of the products minus the total entropy of the reactants. And this is, delta S is what we have over here, 15.77. And the total entropy of the products, what you do is you just multiply them. So here you are given the entropy for CO2, and this is for 1 mole. So you multiply it with 3, so 3 times 213.8 plus 2 times 27.3 minus, now this will be of the reactants. So for Fe2O3 we have 87.4, and for CO, which we are finding, we'll keep as 3x because this is 3 times the entropy for 1 mole. And your final answer shall be 1.00. Right? So this is the final answer for this question. Let's go to the next question. Iron oxide can also be reduced to iron by carbon monoxide as shown. State the effect of increasing temperature on the feasibility of this reaction and explain your answer. Now remember the link between the temperature and the feasibility of the reaction. Your first step to solve this kind of questions is to write the formula again. Delta G equals to delta H minus T delta S. We are given that delta H over here is negative, so we have this one as a negative value. You have delta S as also negative over here. This is negative as well. what we are trying to do is we are trying to find what will be the sign of delta G, because if delta G is greater than 0, then reaction is not feasible. But if delta G is less than 0, then the reaction is feasible. So we have to try to find out what will be the sign of delta G. Now here they say that what will be the effect of increasing the temperature. So what happens when you increase the temperature? The temperature is a positive value normally. Now when you increase this value, what happens is that this term becomes more positive, right? So for example, you have negative T times delta S is negative 15.2. If you increase this, because you are doing a negative times a negative, you are making the answer more positive, right? So this part here becomes more positive. And if this becomes more positive, delta G also starts to become more positive. And if delta G starts to become more positive, then the reaction starts to not be feasible. And hence, the answer for this question will be that the feasibility of the reaction will decrease. And why does it decrease? Is because delta G becomes a more positive value, and hence the reaction will be less feasible. And so that was the last question of question 1. Okay, question 2. Carbon disulfide is flammable and reacts readily with oxygen as shown in this reaction. So we have this normal reaction here. Then they say that table 3.1 shows the enthalpy changes of formation and the standard entropy for the substances. So this is very similar to question 1 if you notice. And here they say that calculate the standard Gibbs free energy change in kilojoules per mole. Try to be careful with the units here. For reaction 1 at 25 degree centigrade, and this is centigrade. So we will have to convert this to Kelvin as well. Now to find the Gibbs free energy change, we do delta H minus T delta S. Remember, this delta H is the enthalpy change of reaction, and we are given the enthalpy changes of formation. So your first step, as again, will be to find the normal enthalpy change. Then we are also given the standard entropy values, so you can do entropy of products minus entropy of reactants to find the delta S, and you have the temperature as well. So because this is very similar to question 1, I have done this for you, and you can see how do we first find delta HR. So the first step was to find delta HR, which is the enthalpy change of reaction. We are given the enthalpy change of formation values, so we are given all of them over here. We have of SO2 to be negative 296.8, but because there is 2 moles, we'll do times 2. For CO2, we'll do this one times 1. For oxygen, because it's an element, it's 0, and for CS2, it's normally 116.7. Then we draw a Hess cycle. Now this is the vector arrow, so this one plus this one gives you this products. And if you're confused about this, just use the tail head rule, that this is the tail, this is the head, and this is the tail, this is the head. So you join the tail to the head. So these two will be the products of this and this. So you just add these up and you get your enthalpy change of reaction as negative 1103.8. So that's our first step, and that's how we get the delta H. Our second step is to find the entropy change, and entropy change of the system is equal to the products minus the reactants. And again, we just fill in the data. We have the entropy of each of these molecules. So when you do the calculations, you get negative 143.2. Just remember to multiply these with the number of moles. So this is per mole, this is for 1 mole. So for example, 248.2, you will do it times 2, because this is 2 moles in the equation. And you should get your total entropy change as negative 143.2. And remember to change the temperature to Kelvin, so we get 278 Kelvin. Then when you add them up, the final answer shall be negative 1061.1. I hope that was clear. Now the next one, carbon disulfide reacts with chlorine to form tetrachloromethane as shown in reaction 2. Calculate the maximum temperature for reaction 2 to be feasible. Again, they always like to ask stuff about whether or not something is feasible or not. And most of the times you have to use this equation again. Delta G equals to delta H minus T delta S. So until now, what do we know about something being feasible? Like, what does the value of delta G have to be for an equation to be feasible? We know that delta G has to be less than 0 for a reaction to be feasible. And more accurately, it's supposed to be represented as less than or equal to 0. Okay? So if delta G is less than or equal to 0, then a reaction is feasible. So let's calculate if whether or not this reaction is feasible or not. We can plug these values in to our equation. So we have negative 261.6 minus T is what we are finding, and we have delta S. But before we continue, look at this. This one, they've kept kilojoules here, and here they've just kept normal joules. So you have to change one of them to be like the same units. Okay, so let's just change this one to become kilojoules. So you divide this by 1000 because you're going from joules to kilojoules. And this will be negative 365.5 divided by 1000. Negative 0.3655 is less than or equal to 0. So what you can do now is you can shift this negative 261.6 in that side and multiply these two brackets here. So negative T times negative 0.3655 will just be 0.3655 T is less than or equal to, when I bring this here it becomes positive, so 261.6. Now you can just divide this by T both sides, divide by this number both sides, and you should get your answer as 715.6. So this is the maximum temperature at which the reaction occurs. We have T is less than or equal to 715.6. The maximum value is this, but any temperature below this, the reaction will also occur. Right, let's go to question 3 now. This is from May-June 2022. Calcium carbonate decomposes on heating. So we have a basic equation here. Then table 4.1 shows the values of the Gibbs free energy change with different temperatures. So we have different temperatures in Kelvin over here and their values for the Gibbs free energy change. Assume the standard enthalpy change and the standard entropy change for this reaction remain constant over this temperature range. Plot the graph of delta G against delta T on the grid. So this is just basic plotting. You look at the points. For example, this one is 9.9 and the temperature is 1050. So you go to 9.9 over here and temperature 1050, you plot it. And you do it for all the other points. And then you finally join them with a straight line. By the way, can we just appreciate this straight line, how nice it looks? Anyways, let's go to Roman 2. Calculate the gradient of your graph and determine the entropy change in joules per Kelvin per mole for this reaction. Show all working. Right now, how do we do this? They want us to calculate the gradient of your graph and they want you to determine the delta S. So there must be some sort of connection between these things. And in most questions, like always, we'll use our equation delta G equals to delta H minus T delta S. Now, what graph is this? This graph, in the y-axis we have delta G and in the x-axis we have T. So this is the y-axis. This is the y-axis and delta T is the x-axis. Now, this is a similar sort of equation to y equals to mx plus c. Because it's a straight line graph, so this obeys y equals to mx plus c. If t is your x, then the remaining part will be your gradient. And delta h is the c. So this part is c and negative delta s will be your gradient. Why is it negative delta s? Because only the t is the x, not negative t. Right? So negative delta s will be the gradient of your graph. So your first step to solve this question is to identify that the gradient is equal to negative delta s. After you do that, you just find the gradient from the graph and you can just use y2 minus y1 over x2 minus x1. You can just choose any 2 points, maybe you choose this point, and maybe you choose this point over here, and you just do the normal gradient calculation. For the gradient calculation, you should get somewhere around negative 160. So you get negative 160 equals to negative delta S. So automatically, to get your delta S, you just divide by negative 1 both sides, and hence you get positive 160 as your entropy difference. And that's it for question 3. Okay, we have reached the last question of this paper, and this is from May-June 2021. The first question says, explain what is meant by the term entropy of a system. Now again, these are just basic definitions. For entropy, we learned that entropy is just a measure of disorder, measure of randomness of a system, right? So you can just write that and you can get the 1 mark. The next question says that place 1 tick in each row of the table to show the sign of each entropy change. So we have to identify if the entropy change is negative, if it's 0, or if it's positive. Remember, the entropy increases if you increase the disorder or if you increase the randomness, right? Let's look at the first one. When NaCl dissolves in water, what happens? So you have NaCl as a solid. When it dissolves in water, it basically becomes sodium aqueous ions and chlorine aqueous ions. You see there's a change in state over here. It's going from solid to aqueous, and aqueous is basically dissolved in water, so it's kind of a liquid. So when you're going from solid to aqueous, you are making the ions free to move, and so you're increasing the randomness and the disorder in the system. So that's why the entropy change is positive, because you're increasing the entropy. And how about when water solidifies to ice? So this time you are going from H2O liquid to H2O solid. So you are actually decreasing the randomness. You are making this thing have more order, right? So the entropy also decreases. So this is negative. Okay. The evaporation of 1 mole of water has a standard Gibbs free energy change of positive 8.6 kilojoules at 25 degrees centigrade. Sketch the graph on the axis to show how delta G changes from 25 degrees until 150 degrees. Okay, so the first point that they've given us is that at 25 degrees centigrade, we have it as positive 8.6 kilojoules. So you can just approximate it somewhere, maybe over here. Okay, now how are we even supposed to identify this thing? What will happen from 25 to 150 degrees? Now here they say that it's the evaporation of water. When does water completely evaporate? When does it completely boil? We know that the boiling point of water is how much? Is 100 degrees centigrade. After 100 degrees centigrade, all water has now become a gas, and all water is now vapor. Okay, so that means that the reaction is feasible after 100 degrees centigrade. Like, there is no way after 100 degrees centigrade that water is not a gas anymore. So what we identify here is that this line must cross over here. So we can sketch a line as something like that, and this is supposed to be a straight line. It's just a very bad drawing, but this is supposed to be a straight line, and it's supposed to go down like this, and it should cross at 100 degrees centigrade, because after 100 degrees centigrade the delta G is negative, and if delta G is negative, which is less than 0, this means that the reaction is feasible. Okay, so but before this 100 degrees centigrade, it's not feasible, right? So it can happen, like water can evaporate, but it's not like all the reaction will happen. Okay, so that's why the line must cross 100 degrees centigrade, and after that, that's when the delta G is negative. The last one says that the reaction between A and B is feasible at low temperatures, but it is not feasible at high temperatures, and we have to reduce the signs of delta H and delta S. This is a very interesting question. You have to activate your Sherlock brains to this. Let's try to do this. The first step is always to write that equation, which is delta G equals to delta H minus T delta S. This will be your first step. Now here we have no other option but to just assume some values, just to try and error, like just try and see if it works or it doesn't work. Now let's say that we take delta H as negative in our first scenario, and we take delta S as positive. When we do that, what will be our delta G? This is a positive value and you're multiplying it with a negative value. So the answer here, from here until here, is negative, because positive times negative. So this will be negative, and then negative plus negative will be negative. So delta G in this case will always be less than 0, always. When delta H is negative, so delta H equals to negative and delta S equals to positive. But the reaction says that it is feasible at low temperatures but not in high temperatures. But here we see that it's always feasible. So this can't be our combination. Let's try another combination. This time let's take delta H as negative and let's take delta S as negative as well. So when we do that, what happens over here? Let's see. Now if delta S is negative, then you are multiplying a negative value with a negative value. You get a positive value. Now you have two values. You have a negative value and a positive value. This is actually our answer, because whether or not the reaction is feasible will depend on which value is bigger. If the negative value is bigger than the positive value, so for example, negative 20 plus 10, then our delta G is negative. But if the positive value is bigger than the negative value, for example, negative 10 plus 20, we get positive 10. So when the negative value is bigger than the positive value, that's when our reaction is feasible. And when it's not, then it is not feasible. Which means that we want this value to be as small as possible. We want negative T delta S to be as small as possible. And for it to be as small as possible, temperature must be as small as possible. So it's feasible at low temperatures, but it is not feasible at high temperatures. And hence, that's why this will be a negative sign, and that's why this will be a negative sign as well. Right? So that is your answer for that question. And that's it. We are done with entropy past papers, and these 4 questions are very good representations of how entropy comes in the exam. Hope you enjoyed it, and I'll see you in the next topic.